Hello everybody. In this video we are going to revise thermodynamics. As we all know that thermodynamics means the study of transfer of heat which results in temperature difference between two bodies. So the whole study of thermodynamics, they are governed by several laws. So the first law is zeroth law of thermodynamics. Zeroth law states that suppose there is a body A which is in thermal equilibrium with body B, and body B is in thermal equilibrium with body C, then zeroth law states that body C will be in thermal equilibrium with body A. Okay. So now let's come to first law of thermodynamics. First law of thermodynamics. First law, it states that the mathematical expression for first law is delta U equals Q plus W, that is change in internal energy of a system equals heat supplied to the system plus work done on the system. According to new IUPAC rules, first law is defined as work done on the system, not by work done by the system. Okay. Now there is a term known as enthalpy. It equals U plus PV. Enthalpy is heat supplied to the system at constant pressure, whereas U is heat supplied to the system at constant volume, because in that case work done becomes zero. Work done becomes zero at constant volume, and Q equals delta U. So since this is the case, since delta U equals heat supplied at constant volume and delta H equals heat supplied at constant pressure, okay, so since W equals minus P delta V, okay, and now consider the temperature is constant, then we get QP equals QV plus delta NG RT, where delta N is the number of moles of products in gaseous form minus number of moles of reactants in gaseous form, or delta H equals delta U plus delta N G R T. Okay. Now see, if CV is the heat capacity of a particular body, if it is a molar heat capacity of a particular body at constant volume, then is molar heat capacity at constant volume, then delta U is NCV delta T, where N is the number of moles and delta T is the change in temperature. And similarly, delta H is NCP delta T with the same arguments, where CP is the molar heat capacity at constant pressure. Okay. Now let's study the conclusions that has been derived from the first law. Conclusions from first law. There are few conclusions that we all have come across after the introduction of first law, and some of them are that suppose there is a case of ideal gas, and if it undergoes isothermal process, so ideal gas undergoing isothermal process, since temperature is constant, isothermal process, since temperature is constant, therefore delta U equals 0, because here delta T will be 0 and here also delta T will be 0, hence delta H will also be 0. So in this case Q equals minus W, because delta U is 0, Q plus W equals 0, so Q equals minus W. Hence heat supplied will be negative of work done. Okay, now the second is in case of isochoric process, where volume is constant, in isochoric process P delta V equals 0, because delta V becomes 0. So from here W equals 0, and hence delta U equals Q. Okay, so and for adiabatic process, for adiabatic process Q equals 0, and in this case implies delta U equals W. Okay, now there's another conclusion which says that if gas expands against constant external pressure and change in volume is delta V. Okay, now if gas expands against constant external pressure, if it expands against constant external pressure and change in volume is delta V, then W equals minus P dV, or del U, that is change in internal energy, equals Q minus P delta V. Okay. Now, as we all know that since this is a molar heat capacity, so CV equals heat capacity of any particular compound divided by number of moles, and there's another quantity known as specific heat capacity. Specific heat capacity, this equals specific heat capacity equals C upon mass. So in this case, in case of specific heat capacity, delta U equals M, that is the mass that we are taking, CV into delta T, and delta H equals M into Cp into delta T. Okay. Now, in case of isothermal expansion, as we have already discussed, that del U and del H becomes 0. Now, work done in case of isothermal reversible expansion. So let's discuss isothermal expansion. Isothermal expansion. So first case is if the process is reversible. So in case of reversible isothermal expression, work done is minus nRT ln V final upon V initial. Okay, and or we can write it as nRT ln P initial upon P final, because using ideal gas law, if temperature is constant, then pressure is inversely proportional to volume. Okay, and now second case, if the process is irreversible, then work done in irreversible process is minus V1 to V2, this is from V1 to V2, external pressure into dV, it simply becomes minus P external. Oh, here it is minus, it becomes minus P external into V2 minus V1, because in this case pressure is so much larger to make the process irreversible that it is independent of volume, or volume is independent of the external pressure, and hence the expression simply becomes minus P external into V2 minus V1. Okay, so let's discuss now adiabatic expansion. In case of adiabatic expansion, if the process is reversible, since we know that the adiabatic expansion is according to this U equals Q equals 0. So from here del U equals W. So in this case del U equals W equals NCV delta T, where CV is molar heat capacity of that particular solid, and delta T is the change in temperature. So in case of adiabatic expansion, and if the process is reversible, then since TV to the power minus 1 equals constant, constant, and PV to the power equals constant. This is the identity of adiabatic process, just like Boyle's law or Charles' law. So in this case, work done equals nR upon gamma minus 1 into T2 minus T1, where gamma equals Cp by Cv. Okay. Now, there is also an expression for irreversible adiabatic expansion. For irreversible adiabatic expansion, work done equals minus R into P external into T2 P1 minus T1 P2 upon P1 P2. This is for 1 mole. Okay. Now let's come to thermochemistry. Now, in case of thermochemistry, as we all know that we deal with the heat of reaction in terms of heat of formation of products and reactants and the bond energy of different species involved in that particular reaction. So in thermochemistry, heat of reaction delta H R equals summation of heat of formation of products minus summation of heat of formation of reactants. And similarly, there are other expressions as well. Heat of reaction equals summation of heat of combustion of reactants. In this case, remember the situation is reversed, minus summation of heat of combustion of products. Or delta H R heat of reaction is also expressed as bond energy, that is delta H of bond energy of reactants minus summation of bond energy of products. So there are some others related expressions as well. So therefore, heat of reaction can be calculated in many ways. Now let's come to entropy. And the second law states that entropy of universe is constantly increasing. Therefore, the entropy, that is degree of randomness of system plus surrounding, should not be smaller than 0 for that process to be spontaneous. Okay, so let's discuss this concept, entropy. Entropy, the formula of ds, that is infinitesimal change in entropy, is dq reversible. If the process is reversible, then heat change in that process divided by temperature. And now for finite changes, as we know that for finite changes, delta S equals q reversible upon temperature. Okay, so there are many ways. Suppose if the solid is heated, now heating of a solid, so in this case delta S equals NCS, that is heat capacity of solid, ln T2 upon T1, where T2 is final temperature, T1 is initial temperature. And if change in state is taking place, change of state is taking place, then in that case delta S equals delta H upon T. Okay. Now in case of ideal gas, there is an expression for entropy change. So in case of entropy change in ideal gas, entropy change in ideal gas, delta S equals NCP, let's write somewhere here, delta S equals NCP ln T2 upon T1 minus NR ln P2 upon P1. So this is the change in entropy whenever an ideal gas undergoes a change in state from state 1 to state 2. That is state from P1 V1 T1 to state 2 P2 V2 T2. Now for an isothermal process, since for isothermal process since T2 equals T1, therefore this quantity will be 0. ln T2 upon T1 will get 0 because log 1 is always 0. Then delta S equals nR ln P1 upon P2, because since this will be 0, then delta S will be minus nR ln P2 upon P1, which we can also write it as plus nR ln P1 upon P2 equals nR ln V2 upon V1, as pressure and volume are inversely proportional. Okay, and similarly for an isobaric process, since pressure is constant in case of isobaric process, since this term is constant in case of isobaric process, so P1 will be equal to P2, hence this term will be 0. And so in case of isobaric process, delta S equals NCP ln T2 upon T1. So there are many expressions which can be derived for an isochoric process. Delta S equals NCV ln T2 upon T1. Okay, so now Gibbs free energy. This is the term which determines the actual entropy of any process in terms of enthalpy. Actual spontaneity of any process in terms of enthalpy and entropy. So Gibbs free energy, it's given by delta G equals delta H minus T delta S. And if we take equilibrium into account, then delta G equals minus 2.303 RT log 10 into K equilibrium. Okay. So let's discuss some questions. The first question, it says that the entropy change for the following processes at 25 degrees Celsius and under constant pressure of 1 atmosphere are as follows. The entropy change means enthalpy change for if CH4 is undergoing dissociation to C plus 4H, then enthalpy change is 396 kilocalorie, and if C2H6 is undergoing dissociation as C plus 6H, it undergoes enthalpy change as 676 kilocalorie. Now they are asking us to calculate CC bond energy in the molecule of C2H6. In case of C2H6, we are asked to calculate CC bond energy. So this is the first part of the problem, and second part of the problem, they are asking us if molar heat of sublimation of carbon and molar heat of dissociation of hydrogen are 171.8 and 104.1 kilocalorie respectively, calculate standard heat of formation of ethane. Okay, so let's discuss first part first. Now it's given that if we write methane in this form, it's given that when this undergoes dissociation as C plus 4H G, then delta H equals 396 kilocalorie, right? So therefore 4 into bond energy of CH equals 396 kilocalorie, because heat of formation of carbon and hydrogen both are 0. Okay, and since here we are considering bond energy, heat of reaction in terms of bond energy, so there are no bonds. In this case also there is no bond, in this case also there is no bond. Therefore 4 into bond energy of CH will be the heat of reaction in this case. So 4 into bond energy of CH equals 396 kilocalorie. So from here, bond energy of CH bond equals 396 upon 4 equals 99 kilocalorie. Okay, now again, there is a second reaction given to us, HCl HC, the structure of ethane, undergoes 2C plus 6H. Okay, now its heat of reaction is 676 kilocalorie, right? Therefore, it means similar to the first part, 6 into bond energy of CH, because 3 bonds are here on this carbon and 3 bonds are here on this carbon. So 6 into bond energy of CH plus bond energy of CC equals 676 kilocalorie. Right. Now 6 into 99. From first part we have got the value of CC bond energy as 99 kilocalorie. So 6 into 99 plus bond energy of CC equals 676 kilocalorie. So from here we get the value of bond energy of CC equals 676 minus 594 equals 84 kilocalorie. Okay, so the first part of the problem is solved. Now let's discuss the second part. The second part says if molar heat of sublimation of carbon and molar heat of dissociation of hydrogen are 171.8 and 104.1 kilocalorie respectively, calculate standard heat of formation of ethane. Okay, so now the bond energy of CC is 84 kilocalorie. Now just looking at the second part of the problem, there is a reaction CS giving us CG and delta H is given to us 171.8 kilocalorie, and H2 in gaseous form, it gives us 2H, and delta H is 104.1 kilocalorie. So let's name this reaction as Sec2. Let's name this reaction as 3. We have named them 2 and 3 because we are going to name this reaction as reaction 1. Okay. Now let's do some mathematics for this reaction. But you know what we are needed to calculate delta H for the reaction. Delta H 2CS plus 3H2 equals C2H6, that is heat of formation of ethane. So its delta H we need to find out. Okay. Now if we do some mathematics, that is if we multiply 2 into equation 2. So if we multiply equation 2 by 2 and then we add it with 3 times equation 3 into equation 3, and then we subtract from it equation 1. Okay, then we get 2 into CS plus 3H2 gaseous minus C2H6 gives 2 into CG plus 6H G minus 2 into C G minus 6H G. Okay, and the heat of reaction will be delta H will be now 2 into equation 2, that is 2 into 171.8 plus 3 into equation 3 into 104.1 minus equation 1, that is 676 kilocalorie. Okay, now rearranging this expression that we have got, these will get cancelled, these will get cancelled, so we will be left with this part of this reaction. So this part of this reaction comes out to be 2CS plus 3H2 gaseous. This will go into product side. This gives us C2H6 gaseous form, and the heat of reaction as if we simplify this further, we'll get heat of reaction as minus 20.1 kilocalorie. So therefore heat of formation of C2 at 6 equals, in gaseous form, equals minus 20.1 kilocalorie. So this is the answer that we are required to get. Okay, so this question has been solved. Let's discuss another problem. The problem says that a sample of 5 mole CO2 is originally confined in 15 decimeter cube, that is 15 liter, at 280 Kelvin, and then undergoes adiabatic expansion against a constant pressure of 78.5 kilopascal until the volume has increased by a factor of 4. Calculate Q, W, delta T, delta U and delta H. The value of CPM for CO2 is 37.11 joule per Kelvin per mole. That is the value of heat capacity at constant pressure, or the molar heat capacity at constant pressure of CO2 is 37.11 joule per Kelvin per mole. So let's see how this problem can be solved. Now, since this is an adiabatic process, okay, since the process is adiabatic, therefore Q will be 0 in this case, and since Q will be 0, since Q will be 0, therefore delta U equals W. Okay. Now work is done against a constant external pressure. Since external pressure is constant, therefore work done will be minus P into external into delta V, which is just the change in volume. So from here the value of work done is minus, let's see what is pressure. The pressure, it is 15 decimeter cube is the initial volume. Okay, at 280 Kelvin the pressure is 78.5 kilopascal. So work done will be minus 78.5 into 10 raised to power 3. Since the pressure was in kilopascal, so we have converted it into pascal. Into, now final volume is 4 into 15 decimeter cube, and initial volume was 15. So change in volume will be 4 into 15 minus 15 decimeter cubed divided by 10 decimeter per meter. This is just to take care of the units. Okay, so from here value of work done comes out to be minus 3.5 into 10 raised to power 3 joule. Okay, now since W equals delta U, so from here delta U equals minus 3.5 into 10 raised to power 3 joule. Okay, now one can also relate adiabatic work to delta T. One can also relate adiabatic work to delta T. Let's see how. As work done equals NCV delta T. Yes, we discussed it a few times before. So from here work done comes out to be N into Cp minus R, since Cv equals Cp minus R into delta T. Okay, so from here the value of delta T equals work done upon N into Cp minus R. So delta T value comes out to be, work done is minus 3.5 into 10 raised to power 3 joule upon number of moles is 5, and Cp we are given as 37.11 minus R. The value of R is 8.3145. Units are joule per Kelvin per mole. Okay, so from here value of delta T equals minus 24 Kelvin. So we have found out three values. Whatever we were given, we have found out Q, W and delta T. Now, and delta U also we have found out. Now we are left with this delta H. So let's see. Now delta H as we know that delta H equals delta U plus delta PV, and now since PV equals nRT and number of moles are constant, so from here this comes out to be delta H equals delta U plus delta plus, since number of moles are constant, plus nR into delta T. Now the value of delta T is minus 24 Kelvin. So from here delta H equals minus 3.5 into 10 raised to the power 3 joule plus 5 into 8.3145 into minus 24 joule. Okay, so from here the value of delta H comes out to be minus 4.5 into 10 raised to the power 3 joule. So this is the last variable that we were supposed to calculate. Now let's move on to the next question. The question says that when 2.25 milligram anthracene, that is C14H10 in solid form, was burned in a bomb calorimeter, the temperature rose by 3.05 Kelvin. Calculate the calorimeter constant, and by how much will the temperature will rise when 135 milligram of phenol, that is C6H5OH, is burned in the calorimeter under the same conditions. We are given with the heat of combustion of anthracene and heat of combustion of phenol here. Okay, now for anthracene, the reaction is C4H10 plus this is C14H10 plus O2 gives CO2 plus H2O. Now if we balance this equation, we will come to the conclusion that the stoichiometric coefficient of O2 is 33/2 and stoichiometric coefficient of CO2 is 14 and that of H2O is 5. Okay, so delta U of combustion is delta H of combustion minus delta N RT. Now since delta N gaseous is at product side, total number of gaseous moles are 14 plus 5 19 minus on product side total number of gaseous moles is 33/2. We are not going to count that the moles of C4H10 because it is in solid form. So this will be minus 33/2. So from here the value of delta Ng equals 5/2 equals 5/2. Okay, now see one thing here, that here total number of H2O we have also counted it, but since H2O is in liquid form we are not going to count it. Okay, so therefore here the total number of gaseous moles are 14 not 19, and hence we are going to take here this as 14 not 19. So from here the value of delta Ng comes out to be minus 5/2. Okay, so now let's substitute the values. You see it comes we are given with delta H as minus 7061 kilojoule per mole. Hence this is minus 7061 kilojoule per mole minus 5/2 into 8.3. Let's take R as 8.3 into 10 raised to the power let's write it at some other place. So this is minus 7061 kilojoule per mole minus into minus 5/2 into 8.3 into 10 raised to the power minus 3 kilojoule per Kelvin per mole into 298 Kelvin. So from here value of delta Cu is minus 7055 kilojoule per mole. Okay, so we have got the value of delta U as minus 7055 kilojoule per mole. Now since we know that Q equals QV, since volume is constant, and hence equals N into delta C U. So total amount of heat transferred at constant volume equals N into change in internal pressure. So this comes out to be 2.25 into 10 raised to power minus 3 gram. The initial amount that we took here was 2.25 milligrams. So 2.25 into 10 raised to power minus 3 gram divided by 172.23 gram per mole. This is the molecular weight of anthracene. If you calculate molecular weight from here, it will come out to be here, so 172.23 gram per mole into 7055 kilojoule per mole. We are going to skip this negative sign because here we have taken the absolute value, okay? So this negative sign has been skipped. So from here the value of Q comes out to be 0.0922 kilojoule. And hence calorimeter constant C equals Q upon delta T. This comes out to be 0.0922 kilojoule upon 1.35 Kelvin, because here the change in temperature is 1.35. Okay, the temperature, this is 3.05. Oh, so here the temperature change is 3.05. So therefore we are going to substitute here the value at 3.05 Kelvin. 3.05 Kelvin. So from here the value of heat capacity or the calorimeter constant comes out to be 0.0302 kilojoule per Kelvin, or C equals 30.2 joule per Kelvin. Okay, now when phenol is used, the reaction is, the reaction is C6H5OH plus 15/2 O2 gives 6CO2 plus 3H2O. And now since delta Hc is minus 3054 kilojoule per mole. Okay, so delta Cu, similarly to the last part, it will be minus into delta NgRT, H minus delta NgRT, and since delta Ng here is minus 3/2, using the same method that we used in the last part. So from here the value of delta U will be minus 3054 kilojoule per mole plus 3/2 into 8.314 into 10 raised to power minus 3 into 298 kilojoule per mole. Okay, so from here the value of delta U equals minus 3054 kilojoule per mole. Okay, now therefore value of Q heat is 135 into 10 raised to power minus 3 gram upon 94.12 gram per mole into 3050 kilojoule per mole. So from here Q is 4.375 kilojoule. Now if we calculate delta T, it is Q upon C, calorimeter constant. Now the value of C that we calculated was 30.2 joule per Kelvin, or 0.0302 kilojoule per Kelvin. So the value of delta T is 4.375 kilojoule upon 30 point upon or 0.0302, or it is 0.0302 kilojoule per Kelvin. So the value of delta T comes out to be around 144.9 Kelvin. So the change in temperature when phenol is used in the same calorimeter is observed to be around 145 Kelvin. So this was supposed to be calculated in the second part of the problem. Now let's discuss another question. The question says that 100 ml of a liquid contained in an isolated container at a pressure of 1 bar. The pressure is steeply increased to 100 bar. The volume of the liquid is decreased by 1 milliliter at the constant pressure. Find delta H and delta U. The value of 1 atm liter is 0.1 kilojoule, that is around 100 joule. Now since the process is isolated, since the process is isolated, therefore Q will be 0. Now since Q is 0 and the pressure is constant, therefore QP equals 0. We can write Q as QP, which is equal to delta H. Therefore this says that delta H equals 0 in this case. Now since using first law of or using the expression for enthalpy, delta H equals delta U plus PV or P delta V, since pressure is constant. So from here, since delta H equals 0, so delta U equals minus P delta V. So from here we can say that delta U equals minus 100 bar into delta V is, since delta V is 0.1, since delta V is 1 milliliter, and therefore the value of delta U comes out to be or here we have taken value of delta V as 1. Oh, the value of delta V is minus 1, because here given in question that the volume of the liquid is decreased by 1 milliliter. Therefore delta V will be minus 1. And hence from here the value of delta U comes out to be plus 100 atm milliliter. Okay. So from here if we divide this expression by 1000, then the value of delta U is 100 upon 1000 atm liter. So this is equals to 0.1 atm liter. Now 1 atm liter equals 0.1 kilojoule. So from here value of delta U is 0.01 kilojoule. So this is the answer for this question. And this question was asked in IIT JEE. In IIT JEE 2004. Because this is an easy problem, hence this was asked in IIT JEE. Okay, so let's discuss another question. The question says that for the reaction 2CO plus O2 gives 2CO2, delta H equals minus 560 kilojoule. 2 moles of CO and 1 mole of O2 are taken in a container of volume 1 liter. They completely form 2 moles of CO2. Now the gases deviate appreciably from ideal behavior. If the pressure in the vessel changes from 70 to 40 atm, find the magnitude of delta U at 500 Kelvin. Here also the value of 1 atm liter is 0.1 kilojoule. We have to assume it. So let's see what can be done in this problem. Okay. Magnitude of delta U. So since we know that delta H equals delta U plus delta PV. So in this case, the unique thing is that volume is constant and pressure is getting changed. Therefore, if we simplify this expression, we will get value of delta H equals delta U plus V into delta P. So from here, delta U equals delta H minus V into delta P equals minus 560. Value of delta H is minus 560 kilojoule plus because the volume is constant and pressure is decreased here, so delta P will be minus and minus will be plus. So plus volume is 1 and the pressure is 30, dP is 30. And now let's convert this is the unit of ATM liter. Let's convert it into kilojoule. So 1 ATM liter equals 0.1 kilojoule. So let's multiply it by 0.1. So whole this expression will be in the units of kilojoule. So from here, value of delta U comes out to be around minus 557 kilojoule. Or if we can take magnitude of this quantity, because in question it is asked to calculate magnitude of delta U. So from here delta U equals 557 kilojoule. Okay. So this was asked in the problem. So since this is also a very easy problem, this was also asked in IIT JEE 2006. Okay. So now let's discuss another question. The question says that calculate delta S for the system when the state of 2 mole diatomic perfect gas molecules is changed from 25 degrees Celsius and 1.5 atm to 135 degrees Celsius and 7 atm. Okay, so let's see how this problem can be solved. Now the unique thing in this problem is to realize that however the change is occurring, delta S has the same value as if the change happened by reversible heating at constant pressure. Step 1, if we take the step 1 as the reversible heating at constant pressure, followed by reversible isothermal compression, because delta S is a state function, not a path function. Okay, so if we take the system from state 1 to state 2 via 2 steps, that the step 1 is reversible heating at constant pressure. Reversible heating at constant pressure, and step 2 is reversible isothermal compression. Reversible isothermal compression. Okay. So therefore delta S will be the change in entropy due to step 1 plus change in entropy due to step 2. Now for step 1, okay, so delta S1 will be integration of dq reversible upon T equals integration of Cpm dt upon T. So this will be equal to Cpm ln T2 upon T1, or T final upon T initial. So from here value of delta S1 equals 2 into, since the gas is diatomic, it is given in the question that 2 mole of diatomic perfect gas. So in case of diatomic gases, value of Cp is 7R upon 2. Okay, now if we convert this into molar heat capacity, so since this is for 1 mole, hence if we are considering molar heat capacity, then we will multiply it with total number of moles, because the number of moles is more than 1. So 2 into 7 upon 2 into R, that is 8.3145 into ln 135 plus 273 upon 25 plus 273, and the unit is joule per Kelvin. So from here value of delta S1 equals 18.3 joule per Kelvin. Okay, so now in case of second step, for step 2, delta S2 equals integration of dq reversible upon T equals simply q reversible by T. Okay, now Since process is isothermal, therefore delta U will be 0 and hence Q reversible equals minus W equals nRT ln P1 upon P2. Initial pressure upon final pressure. So therefore from here delta S2 equals nR ln P1 upon P2. So if we solve it further, we get the value as A2 into 8.3145 ln 1.5 upon 7. Initial pressure was 1.5 atm and the final pressure is 7 atm. So from here the value of delta S2 is minus 25.6 joule per Kelvin. Therefore total value of delta S is delta S1 plus delta S2 equals 18.3 minus 25.6 joule per Kelvin. So from here the value of delta S is minus 7.3 joule per Kelvin. Okay, so entropy of system, here we can see that it has got negative magnitude. Now a question can arise in the mind that if the magnitude of entropy is negative, how the process is spontaneous? This process should not be spontaneous. But remember that if you analyze this solution clously, you will come to a conclusion that the heat lost in step 2 was more than the heat gained in step 1, resulting in a resulting in the net loss of entropy. Or in other words, we can say that the ordering represented by confining the sample to a smaller volume in step 2 overcame the disordering represented by the temperature rise in step 1. So this negative value of entropy change is allowed for the system as long as the increase in entropy elsewhere results in total increase in entropy for universe greater than 0. So as long as delta S total is greater than 0, this reaction is spontaneous or allowed, we can say that, or allowed. So it depends on the entropy of surrounding, how much it is allowed or how much it can be made spontaneous. So now let's discuss another question. The question says that 1 mole of monoatomic ideal gas expands adiabatically at initial temperature T against a constant external pressure of 1 atm. Okay, now from 1 liter to 2 liter, find out the final temperature. Now since we know that work done at constant external pressure equals P external into V2 minus V1. Its value is negative. Now in case of adiabatic condition, since delta U equals 0, therefore W equals delta, since delta Q equals 0 in adiabatic conditions, Q equals 0, therefore delta U equals W, and hence minus P external into V2 minus V1 equals 3 upon 2, since the gas is monoatomic. Okay, so 3 upon 2 into R into T2 minus T1. Now if we solve this expression further, we get something like T2 equals T1 minus 2 upon 3R. Okay, because this expressions, these get compensated here. These get compensated, and on solving this expression, we get the value of T2 as T1 minus 2 upon 3R. Okay. So this problem appeared in IIT JEE. in IIT JEE 2005 screening. This question appeared in screening part. So here, since the external pressure is 1 atm and V2 is 2 liter, V1 is 1 liter, so this equals 1. On solving, we get T2 equals T1 minus 3R. So this problem is very easy. Therefore, you should have absolutely no problem in solving this question. So now, let's discuss another question. This is the last question of this video. The question says the heats of formation of H2o liquid state is minus 285.8 kilojoule and standard molar entropies in joule per Kelvin are S of H2o is 69.9, H2 is 130.6, O2 is 205. Now calculate the standard free energy of formation of liquid water at 25 degrees Celsius. Okay, now standard free energy of formation of liquid water at 25 degrees Celsius. Let's see what kind of reaction is taking place. Whenever a water is formed, the reaction is somewhat like this. That's half O2 gaseous form gives H2O liquid form here. Okay, so now delta S, as we know, by using delta S equals in this sigma of delta S of products minus sigma of delta S of reactions. So delta S equals S naught H2O in liquid form minus S naught H2 in gaseous form minus half of S naught O2 in gaseous form. So this the value of delta S comes out to be 69.9 minus 130.6 minus 102.5, because delta S naught of water is of H2 is 130.6, of water is 69.9, and S naught of O2 is 205, which on dividing by 2 comes out to be 102.5. So from here, value of delta S naught is minus 163.2 joule per Kelvin. So here the units are in joule per Kelvin. Now since we know that delta G naught equals delta H naught minus T delta S, now we know the value of delta H. The value of delta H is minus 285.8 kilojoule. Okay, so now let's solve this. Delta G comes out to be minus 285.8 kilojoule minus 298 into 163.2 upon 1000, because 163.2 is in joules, so to convert it into kilojoule we have divided it by 1000. Now if we solve this further, we get the value of delta G naught as minus 285.8 kilojoule minus plus 48.6. Since this is in minus, therefore this will be plus 48.6 kilojoule. So this equals minus 237.2 kilojoule per mole, or to write it more clearly, from here the value of delta G is minus 237.2 kilojoule per mole. So this was the application of this formula, delta H minus T delta S. But remember that the problems in examination based on Gibbs free energy comes with a combination of electrochemistry and equilibrium part. So therefore do have command on equilibrium and electrochemistry as well as on thermodynamics, because the problems come somewhat linked from all of these chapters. Hence, since here we have got the value of delta G, now this problem has been solved. So that's all with this video. See you in the next video.